All right. Okay. So in this lesson, we are going to be talking about inverses of exponentials. Okay. So we really have just one objective that we are going to be touching on in this lesson, and it's we're going to construct representations of the inverse of the exponential function when the initial value is 1. So we're going to be starting blending. We're going to start blending some of our ideas together from the first part of the unit to this part. So there's not a lot today that we're going to cover that is like new information. It's more like using the old information and like applying it to discover some new things. Okay. So when we talk about an exponential function with a value of 1, we're talking about just your basic exponential function. Okay. F of x being b raised to the x. Okay. Now we know that b cannot be negative and it also cannot be 1. So we're considering the scenarios of both growth and decay. Now, when we think about an exponential function, let's start off by thinking about its domain and its range. What is the domain of a exponential function? What type of numbers can we plug in?
All real.
All real numbers. Good. Let's do this in green today. Great. So we know that the domain of an exponential function is all real numbers, right? We can plug in anything, right? Negative numbers, positive numbers, fractions, irrational numbers. What is the range of an exponential function?
Bigger than 0.
Good. Y has to be bigger than 0. Because what does an exponential function have?
An asymptote
Good.
0.
Good. So that's why we have to do an exponential function. The range is, all those positive values. Okay. Now when we think about the inverse from 2.8, right? In 2.8, we talked about inverses, right? We talked about exponential stuff. We did compositions, then inverses. What is true about the inverse of any function? How do you find the inverse?
With the y and the x.
Good. Now, the way that we're able to write this is, I know it's going to look a little weird because I'm going to use function notation. This is the same thing as x equals b raised to the f of x, right? That'd be the flipping of the x and y's. If you want to write x equals b to the y, that's fine too, okay? Because we know f of x and y, they're the same thing, right? All right, now, yesterday, we talked about how we can write exponential equations like this using, like, how else can I write x equals b to the y? What's another way of saying right that?
Log base b of x equals y.
Ooh. Y equals log base b of x. Or we could write it as f of x equals log base b of x. Let's keep on going with this train of thought. If the domain of an exponential function is all real numbers and the range is y is bigger than 0, what is the domain of an exponential function? Ooh, domain. X is bigger than 0. What is the there's the answer. What's the range of a logarithmic function? All real numbers. If we understand the properties of an exponential function, we will automatically know the properties of a logarithmic function because they are inverses. Okay. Now, I'll just point out here, going from here to here and backwards, that this is what we did in the last lesson, right? That whole rewriting. Okay. So what we're going to do today is we're going to construct inverses of exponentials. This lesson is essentially like logarithm basics, essentially, because we'll talk about logarithms again in lesson 11. Okay. So let's look at example 1. Oh. Given the exponential function f of x equals 2 to the x, we're going to graph its inverse and describe any properties of the graph. Okay. Now, when you are, what just happened here? Oh shoot. Yeah. Just. All right. Now, when we think about graphing an exponential function, right, there are 3 values that we plug in. And I'm going to put this over here. -1, 0, and +1. When we plug in these 3 values into f of x, we get 1/2, 1, and 2. Let's go ahead and graph f of x. So -1, 1/2, 0, 1, 1, 2. Okay. This is that exponential function, okay? F of x. Now, we're getting this 1/2, 1, and 2 because these values, when we plug in -1, will always follow the pattern 1 over b, 1, then b. Okay. This is the pattern that these numbers will always follow when we think about that exponential function. Now, we want to graph its inverse. Let's start with the inverse right here. What did we say was the main thing we did when we graphed inverses of functions?
Flip the y to x.
Good. So for my inverse, I'm going to do this in blue. If I flip these points, then I would get 1/2, -1, 1, 0, 2, 1. Now, when I do this, I have a logarithm. Man, that breeze feels good, doesn't it? Now, when we deal with this, there are 3 things that are important to point out. Now, these points, right, these are the 1/2, -1, 1, 0, and 2, 1. Does anybody remember across which line inverses are a reflection over?
Right there, like return.
Ooh, there
X.
Y equals X.
Yeah, that.
it is y equals x. It is y equals x because with an inverse, we are essentially saying the y's equal x and the x's equal y. So we're flipping them. So you'll always find that is a reflection over y equals x. Okay, remember that's true for any inverse.
Is it always that? If there's like a translation or something, would it still affect it? Or
Yes. Yeah. Yep. We'll talk about these transformations later.
okay.
We'll do that in lesson 12. We're gonna do like logarithm properties. Now, let's think about what this function is algebraically. So if f of x is 2 to the x, the inverse would be I want to do that in blue since we're talking about the blue graph. Would be that, but if I rewrite it, it'd be f of x equals log base 2 of x. Okay. So that is the inverse of my exponential function. One thing that might be also worth be pointing out is remember that kind of that inverse notation. This is the inverse of f. Okay. So you can say the inverse of f or f of x. It's tomato. It doesn't really matter. Okay. Just because like that inverse of f, that's describing the relationship. But like f of x is like its own function. So maybe it'd be better if I put like g of x. Because I'm not saying that these are the same. I'm just saying how you would write the function. Yeah. Okay. Now, so then we already kind of talked about like with these functions with no transformations, the domain and the range are going to be the same. Okay. Domain x bigger than 0. You could write this as 0, comma, infinity with parentheses, okay, using that interval notation. You could do that. And then the range, right, is all real numbers. You could do it like that. Now, when then thinking about, these coordinate points, the coordinate points are relatively pretty, like, I think if we remember this pattern for the exponentials, the pattern for the logarithm is just as easy as well. Where you would have like 1 over b, comma -1. There's always 1, 0, which is nice. And then b, comma 1. Okay, so you're always going to have like this pattern of numbers. Okay. All right. So there's kind of that first representation. Okay, we're we're representing this graph of the inverse of an exponential with initial value of 1. Now let's do it algebraically. Okay. So now we're going to do we're going to find the inverse of each of these functions. Okay. So we have 3 of them. No, and let's go back to the green. What kind of we want each color? All right. So A is g of x equals 4 raised to 3 raised to the x. Okay. So this is actually this can be interesting. Okay. Let me show you why. So when I first switch these, it's going to be x equals 4 raised to the 3 raised to the, and since we're dealing with the inverse, I'm going to put up here the inverse of g. So it's like I have an exponent of the exponent. Okay. Now, the first thing I want to do is I want to create that base of 4 to be a base of a logarithm. So this is going to change into 3 raised to the g inverse. Let's see if I can put that a little better. Yep. Equals log base 4 of x.
Is this going to be a log over a log?
Kind of. So
we get there? I'm sorry.
yeah, no. So to go from here to here, I'm using that definition of a logarithm to an exponential. So like yesterday, we remember how we talked about b raised to x equals y is the same thing as log base b of y equals x. That's what I'm using. It's just this exponent has an exponent. So what's going to end up happening is a logarithm inside of a logarithm, which makes sense because I have an exponent inside of an exponent. Knowing how to create an inverse with some of these complex forms using the definition of exponential to logarithm can be really helpful. So because we're going back to we want to be comfortable with how do we rewrite exponentials using logarithms. It just so happens with this one you're doing it twice.
And you can't just divide by 3.
No, because we're not multiplying. Because this is 3 raised to the inverse of g, not 3 times the inverse of g. Yep. Yeah, that would be a little bit different. If this was 4 raised to the 3x, that'd be a little bit different. But this is 4 raised to the third raised to the x. So, and there's no way to like change that base of the 4. So, all right, and now let's go backwards. New color, orange. M of x is log base 6 of log of x. Now this is a common log, okay? X is log base 6 of log of the inverse of m. Okay, this is essentially what it's going to be. Now, let's do this. There are a few different ways we could go about doing this problem. Notice how this is like what we ended with in A. I have a log of a log, log of a log. Notice how that log of 3 being on the outside was the base of the exponent of the to the exponent, and how 4 was the initial base. Yeah. So let me ask you, with this one, will the initial base be 6 or 10?
10.
It will be 10.
10.
Because if I look at this pattern, that 4 becomes the base of the most inside log. So the most inside log here is 10, the natural common log. So this should be going to have 10 as its base. And then the next base of the exponent is 6 raised to the x. That's one way to do it. to see some of the pattern, here is the other way you could do it. You could use the definition of logarithms to exponentials. For instance, 6 raised to the x equals this expression. Okay. Okay, so that's the answer, but you could go from here to here, and then here, 10 raised to 6 raised to x equals the inverse of n. Here, raised to that equals that. Same answer. Just using just a different method. Now let's look at this last one. C is k of x is log base 6 of 6 to the x. So this inverse, let's go to purple. This inverse is going to be x equals log base 6 of 6 raised to the inverse of k. So how could I rewrite this one?
6 raised to x over log. Hold on. 6 equals 6 raised.
So, sorry, can you say that again?
6 raised to the x equals 6 raised to the k minus 1 x.
So actually going to y.
Yes, it does. The inverse of k
Is x.
is x. So this is to show us something really important. When you take the log, we've been talking yesterday. We were talking about how a logarithm undoes the unknown exponent. So when I have a logarithm of a base, and I'm taking the logarithm with the base, and the bases of the logarithm and the exponential piece are the same, it just becomes the exponent. So like if I did log base 2 of 2 raised to the 3x plus 1, if I did that, the base of the log and the base of the exponent cancel out. So it just becomes 3x plus 1. Because it's like if you're square rooting x squared. They cancel out. So it's whatever is, so with that, it's whatever on the inside of that squared. The same thing would happen with something like this. Your base of your exponent and the base of the log are the same. So you would get 3x plus 1.
Can you raise something to the log? Like a coefficient to the log or something? Like,
Do you mean?
that's what it looks like right there. I don't know if you could use something.
Yes. Yeah, you can have a logarithm and an exponent.
Yeah.
Yep.
You just have to put in there.
Yep. Totally.
How would you go about doing that?
Chances are, if you do see something like this, the bases are going to be the same. So that you can just be like, they cancel out.
Yeah.
Yep.
Can there be like log base 2 raised to the x? Like log base 2 with the exponent of x 3.
Like an x right there.
Like an exponent on the base. log base.
Like the base of the logarithm is a variable? Do I come write it?
Yeah.
I'm trying to picture where you're trying to.
Like log base 2 of x of like 3.
No, you'll never have. And yes, you will never have. You would, okay? Theoretically, yes, you could. I've never seen that.
Okay.
Yeah, hypothetically you could, but like here, then the x would have to be make that x would have you would have to make sure that the base of the logarithm is bigger than 0, but not 1. So I think the graph would look a little weird.
Okay.
But yeah.
Can I use the question?
Yes, you may. Yeah.
Just take a shortcut. Sorry, it's not a mathematical question. Sorry. Actually, hold on.
Do you mean the shortcut through the electrical room?
Yeah, this is short. Yeah.
All right. We have about 10 minutes. We have about 10 minutes left. Okay. We are going to talk about tables. Okay. So like I said yesterday, the last place that you're going to be asked to look at a table to determine the pattern is a logarithmic function. Now, right here on the right-hand side, left-hand side, you see an exponential function, right? 10 to the x. This is lighter red. Notice here, this has a common ratio, right? Yeah? Multiply by 10. We know that is the base of the exponent. That's that. Going back to the R, going back to the B, it's all there. Notice that with this table, we have a constant proportion in the output, right? We learned that back in lesson 3 with exponential functions. That with an exponential function, you have a constant proportion in the output. And I'll also just say, let's go back to that phrase, consecutive, equal length, input value, interval, right? It's that same language that we even saw back in unit 1. Okay. Now, the inverse, right? 2.8. 2.8, the inverse. G of x is now 10 to the x. That is like my input column. My x's are my output column. 10, 100, 1,000, 1, 2, 3. What I'm about to show you is revolutionary. Just kidding. It's not. If we're flipping the x and the y's, a logarithm will have a constant proportionality in the input. Right? I mean, that only makes sense that if I'm flipping the x and y's from an exponential to a logarithmic table will have a constant proportion in the input. But then they will have consecutive, equal length, output value, intervals.
So the output becomes the input, and the input becomes the output.
Exactly. That was an awful. That's better. There we go, Quinn. All right. So So if we can recognize the pattern in a log and an exponential, we will recognize the pattern with a logarithm. Okay, it'll just be flipped. Okay, this is true of any type of logarithmic table. So, example 3, or last example, we've got 5 minutes. Let's do it. Determine if the table below represents an exponential or logarithmic pattern. Explain, then write the function. So let's look at A, g of x. 4, 5, 6, 16, 32, 64. Is this exponential or logarithmic?
Exponential.
It is exponential. Since output value is, or output value has constant proportionality of what?
2.
Good. And this is one of the lessons. I'm bringing with me from that AP reading. You have to put the number. You have to put the number. You can't just say output value has constant proportionality. You have to put the number. Now, one thing that I will say we did do for kids is that if they showed times 2, times 2, times 2, times 2, if they showed the multiplying by 2, they did earn the point for explaining that pattern. Now, let's write the function. Oh no, I don't know what x, we don't know what g is when x is 0. No worries. G of x is 16 times 2 raised to the x minus 4. We have done this already back in 2.
So that's how I find it what it was to 0.
You don't need to find what it is at 0. It just says write a function. We did. It is that straightforward. All right, how about B?
Logarithmic.
It is logarithmic.
So basically, if it's constant proportionality or when it equal like angles on the right side, it's logarithmic.
Yes.
Log against the
Yes. Logarithmic.
Logarithmic.
on the left next page.
Yes. And that's the thing that does separate these from linear and quadratics, right? Linear and quadratics, it's based off of addition or subtraction. Here, it's multiply. It's based off of multiplying. So this is logarithmic since input value has constant proportionality of 5. Of 5. Now this one, what is nice about this is that because we've not dealt with logarithmic transformations yet, like A, this is just log base 5 of x.
That's it.
Yep. Because I noticed that it's 1, 2, and 3. Okay. Notice times 5. Times 5. So I know that that's my base. And then how about C? This is also logarithmic. Since input values has constant proportionality of, what does this have a constant proportionality of?
2.
Good. So this is, so n of x, I know that we don't have the value for 1 here, but n of x is log base 2 of x.
For logarithmics, if like it's the opposite is 1, like for b, it's like 5, 1.
Yeah.
If you have that, would it always be like the logarithmic of that?
Yes. Yeah. Well, it'll be the like times 5 because like here it's times 2, so I wouldn't want to put the 4. But like yeah, if you have the 1, the output value of 1, it is that input value that is the basic one. Okay.
And it doesn't matter if you have a fourth term in different two.
No, it does not matter because it's this constant proportionality of the input that becomes the base. So like here, 4, 8, 16, I'm multiplying by 2. All right, your homework is 10 questions.
No.
This is due on Monday.
Take log base there.
Indeed it does. Thank you, you too.
Essential. Like a weed.